Alright, this video contains the solutions for the Chapter 2 review problems. These first four limits refer to this graph, which might look familiar. It's from your book. So the limit as x approaches infinity of this function, it looks like as we approach infinity that it's getting closer and closer to 2, that there's a horizontal asymptote. So when you're thinking about things as functions, limits at infinity are really referring to, is there a horizontal asymptote or not? So that looks like it's 2. The limit as x approaches negative infinity looks like it's coming down. I hope you could tell from the copy here, but I would say that looks like it's creeping down to 1 from above. So it has two different horizontal asymptotes there. Here, as x approaches 0, it looks like there's just a point there. Maybe it's at about 1.5 or so. We just have to estimate that from the graph. And then finally, as x approaches 3, both sides are plunging down to negative infinity. They're both on the same side, or they're both going to the same version of infinity, so we can report an answer instead of does not exist. So if you did have does not exist here, that would be marked wrong. And the actual point there is in the wrong place, but that doesn't matter. It's about what's happening as we get closer and closer to 3. All right, number 2 looks like a factor and cancel. But before we do that, you should always just plug that in. Negative 5 squared is 25, so that is 0 on the top and 0 on the bottom. So it is a 0 over 0. So if I factor, I get the limit as x approaches negative 5, x plus 5 over x minus 5 over 2 times x plus 5. The x plus 5s, which were causing the 0 over 0 problem, cancel. And now I can plug in the negative 5. So negative 5 minus 5 over 2, which is equal to negative 5. Sorry, negative 10 over 2, I meant to say. And then here, as x goes to infinity, so this is as x blows up, I have polynomial expression over polynomial expression. So wherever the highest exponent is, that is what is going to determine the behavior of this. Since the highest exponent is unmatched on the bottom, that's going to drive this down to 0, because this will get bigger faster than the top. So that is going down to 0. Limit as x approaches infinity of this crazy expression. When we have an expression like this, we want to look at the inside first. So as x goes to infinity, I've got squared on the top and bottom, so it's the coefficients of those. That's what matters. So it looks like this expression is going to 1/9, right? The 5 and the 1 fade off into obscurity. So this is effectively asking what's log base 3 of 1/9. So snuck in a little bit of logarithm review for you here. That's like asking, what do you have to raise 3 to get 1/9? 3 to some power is equal to 1/9. Well, 3 squared would give you the 9, and if you want to flip something over, that's what negative exponents do. So 3 to the negative 2 is equal to 1/9. All right, number 5, as x approaches 2, let's see, we plug in the 2, that gives me 9 over 5, and that's not a 0 over 0. So you always have to check. You never know when it's just going to be a limit that you can plug in the number. Here, this is from section 2.6. The sign of 4x over 3x as x approaches 0 is just 4/3. You can go back and review the 2.6 notes and examples if you need some support for that. As x approaches 3 here, that's 9 minus 12 plus 3, that's 0. It is a 0 over 0, so that's the same as the limit as x approaches 3. That factors into x minus 3 over x minus 1 over x minus 3 times x plus 3. We're expecting the x minus 3's to cancel. That was causing the 0 over 0 problem. Then I plug the 3 in, I get 2 over 6, which reduces to 1/3. Number 8 looks like might have to multiply by a conjugate here. Let's just make sure it's 0 over 0 first. Plugging 3 in, 3 times 3 is 9, square root of that does give me 0, and so does that. So I'm going to go ahead and multiply the top and bottom by the conjugate of this. Of course, I have to multiply top and bottom by the same thing. When I multiply this minus this times this plus this, that turns into the difference of two squares. So that gives me 3x minus 9 over x minus 3 times the square root of 3x plus 3. And notice that 3x minus 9 is the same as 3 times x minus 3. We know that we want the x minus 3 to cancel out, right? That's what's causing the 0 over 0 problem. Now I have 3 over that, so I should be able to plug my 3 in. 3 times 3 is 9, the square root of that is 3, plus 3 is 6, and 3 over 6 is 1/2. This is another one of those problems from section 2.6. Like number 6, as long as it's just sines and tangents involved like this, we know that in fact it is just going to be 4/9. Again, if you want more detail or why that works, there are examples in the 2.6 notes video. Here's another composite one. We need to figure that out first. As x approaches infinity, so there should be parentheses around that to make that more clear. Sorry about that. X plus 1 over x minus 1. As x goes to infinity, this approaches 1. Right? It's like x to the first, x to the first. The 1's fade off into obscurity. And so this is effectively asking what's the sine inverse of 1? And what is the sine inverse of 1? Well, that's a y-coordinate on the unit circle, and the angle that goes with that is pi over 2. Here, another 2.6 problem, but I've got an extra x on the bottom. So that's like, we could rewrite that as sine 5x over x times the extra x there, the 1 over x here. This would be going to 5. This, as x goes to 0, is going to go to infinity, and 5 times infinity, by any accounting, is going to be also infinity. And actually, you know what? Because we don't have specified here which side, this is 1 over x. It would depend. It would go to positive infinity if we went to 0 from the positive side, or negative infinity if we went from the negative side. So really, more correctly, we should say that it does not exist. And 5 times does not exist also. Does not exist. I might let you off the hook with that, putting infinity for that one, but does not exist is a little bit more correct answer there. Here, as x approaches infinity, we have highest power, top and bottom. Coefficients are 1 over 3. Approaching 1 from the positive side here, that would give me about 6 on the top, positive 6, and 1 from above means something a tiny bit bigger than 1. So a little bit bigger than 1 minus 1 is a very, very tiny but positive number. So I've got positive divided by positive. That's going to give me positive infinity. And note that it would be negative infinity from the other side. As x approaches 3 here, I have 6 over 0, but because it doesn't have the plus or minus, we'd have to check both of those. And if you plug in something a little bigger than 3, that's going to be very small but negative. And on the other side, a little bit smaller than 3, it'll be very small but positive. So it looks like the two different sides are approaching infinity in two different directions. Something like, looks like something like that. And that means that this is a does not exist. Number 15, we have sine squared, so let's see, we need to split that up into sine of 2x over 3x times sine 2x over 3x, like that. That's what this means, and that would be 2/3. times that would also be 2/3. So that would give us 4/9. Number 16 is a limit at infinity. We've got highest power on the top, which means this is going to blow up to infinity. Right? Highest power wins, and it's only on the top. Number 17, looking now for values where each of the following functions is. Is that grammatically correct? Find all values where each of the following functions are continuous, is continuous. Sorry about that. So what about this? That's just a polynomial. So where is that continuous? You could write continuous everywhere, or you could write it as the interval from negative infinity to infinity. That's where it's continuous, everywhere. How about this? This is continuous everywhere except for what makes the bottom equal to 0, -2 and 2, when you factor that. So in interval notation, you could write it, it's continuous everywhere except, you could also write it like this. It's continuous from negative infinity to -2, from -2 to 2, and from 2 to infinity, right? That covers everything except -2 and 2. How about this one? Well, when you've got a square root sign here, this function, you can't take square roots of negative numbers, so anything less than 5 is going to make what's underneath the square root sign negative, and we can't take the square roots of those things. And also, since it's on the bottom, we can't let it be 0 either. So effectively, we need to make x minus 5 greater than 0. Not greater than or equal to, because then we'd be dividing by 0. So I need x to be greater than 5. So this function is continuous from 5 to infinity. You could write it like that too, that's fine. But in the interval notation, that would look like this. How about this piecewise function? Well, it looks like the pieces are just little polynomials, a straight line and a parabola, so those don't have any issues unto themselves. The only possible issue is when it crosses over from being one piece to the other. So plugging the 2 in here, that gives me 3. Plugging the 2 in here, that gives me 4 minus 1, that's 3. So it looks like the two pieces do in fact link up, and that means it's continuous everywhere. In number 21, value of k that makes the following function continuous. Just like what we did here, if it's going to be continuous, that means when I plug 1 into this and when I plug 1 into this, I need to get the same thing. So plugging 1 in here would give me 3k times 1 minus 5, or in other words, 3k minus 5. Plugging 1 in here would give me 1 plus k. And if it's going to be continuous, those two things have to be equal. And now I will do a little bit of algebra 1. And get that k must be equal to 3 for that to happen. How about this one? This one is a little bit more challenging, I think. I'll give you a little nudge and then you can pause and try to continue from there if the little nudge helps you. So we want to find values for a and b that make this function continuous everywhere. Well, let's see. If it's going to be continuous everywhere, then the first thing we might realize is the only kind of issue we could possibly have is a hole. So this would have to be, if it's going to be continuous everywhere, a function that has a hole, and this is the patch of the hole. Right? That's the only way. If there's a vertical asymptote, if this x minus 7 is causing a vertical asymptote, that's not fixable. So that means that the x minus 7 factor must cancel out with the top of this. It has to, right? If it doesn't, that means we don't have a hole, we have a vertical asymptote, and there's no way it can be continuous everywhere if that's the case. So that means here, think about that. What does a have to be so that the x minus 7 can cancel out? The only possible choice for a, did you pause? Okay, you're back. The only possible choice for a is 3, right? It would have to be 3 times, and then you could factor the 3 out, right? If that were 3, the top would be equal to that over x minus 7, and then those would cancel out, and you'd get, there's a hole at, when you plug in 7, there's a hole at 3, so that means it's the point 7, comma 3. And that means that this, since the hole is at 7, comma 3, that would have to be equal to 3. So I think we have A must be equal to 3, and 2B must be equal to 3. So B must be equal to 3/2. A has to be 3, B has to be 3/2. Number 23. Sketch a function that includes the points -2, -1, and 1, 2, but does not cross the horizontal line at y equals 1. There's that horizontal line. So we want to sketch a function that goes from here to here, but does not cross that line. So there's different ways of doing that. You might have sketched something that had a hole in it, right, that went from here to here like that. You might have sketched something that had a vertical asymptote. You might have sketched something that had a jump in it. You could even sketch it like that and then like put the point in the right place. But however you're going to get from here to here, you certainly have to be discontinuous somewhere, right? You have to have a hole, jump, or vertical asymptote to do that. And then the follow-up question here, could your function be continuous and not cross this line? And the answer is no. Why or why not? I think the best explanation, referring to things that we've studied in this chapter, would be because of the intermediate value theorem, right? In other words, if f, the function that you're drawing here, if f was continuous, it would cross every y value between -1 and 2. And of course that would include our line at y equals 1, because the 1 is in between -1 and 2. So can't do it and still have a continuous function. All right, last couple of questions here refer to this function, which looks like it's just dying to be factored. So let's do that. So f of x is equal to x plus 5 times x minus 5 over, factor out an x from those, and then x minus 5 is x minus 1. All right, that's what you get when you factor that. So let's see. Notice that there's a hole at 5, and there are vertical asymptotes at 0 and 1, right? Hole here because that factor cancels out. Vertical asymptotes anywhere where the bottom's equal to 0, and it doesn't cancel out. So let's see. Find each of the following limits. How about 1 from the positive side? So imagine a tiny little number, a little bit bigger than 1. That would make this positive. This would be positive. This would be the tiny thing going to 0. So positive, positive, and 0 on the bottom means we're going to positive infinity. How about as x approaches 5? Well, the 5 cancels out, and that would give me 5 plus 5 is 10 over 5 times 4. That's 10 over 20, or 1/2. As x approaches 0, we have to check both sides of 0 because that is at a vertical asymptote. And what you're going to find is when you plug in a number a tiny bit bigger than 0, you're going to get negative, right? That would be positive, negative, and positive. And when you plug in a number a tiny bit smaller than 0, you're going to get positive, negative, negative. So we get two different limits. We get the limit as x approaches 0 from the positive side is negative infinity, and the limit as x approaches 0 from the negative side is positive infinity. So that means our limit does not exist. Right? It's coming up to its asymptote on the two different sides. One to positive infinity, one to negative. And then finally, what's the limit as x approaches infinity of this function? Well, there we just look at the highest exponents. The highest exponent is on the bottom. That means the bottom wins and gets bigger faster than anything else, so that's going to 0. And I think we kind of already answered number 25. F of x has 3 discontinuities. Classify each as a whole jumper vertical asymptote. We know that at x equals 0 and x equals 1, we have vertical asymptotes, and at x equals 5, because that cancels out, we have a whole. Right? You can't really get jumps unless you make a piecewise function, or I think we saw a couple examples where you can do it with absolute values. But otherwise, we're going to be looking at wholes and vertical asymptotes if all we can do is factor and possibly cancel.